Good afternoon, everyone. My name is Jingyuan. Today, I want to talk about the project that we've done to help improve the fidelity in archive web pages. But I guess most of us probably have very few idea about this topic, so I'll start by giving some context. And let's start by talking about planning my trip to Seattle. Well, I guess all of us are coming here for the conference. Some of us might want to spend some extra time afterwards tripping around the city. For these folks, I would recommend Mount Rainier based on what I've read on this Wikipedia article. And while I'm reading through this article, there's a paragraph talking about this cool volcanic glacier cave network within the Mount Rainier with 2 miles of passages. We need to learn more. I click on this reference link 38. But unfortunately, this is what I got. On the live web page, there's a 404 showing me that the page no longer exists. So what can I do? Well, Wikipedia folks actually also realized this. So what they try to do is they try to find if there's any historical snapshot of this page on Internet Archive Sweeper Machine, which is one of the largest archival services. And unfortunately, there are a bunch of them. So they include one of them in the link of this reference link 38. If you click on that, you will be able to see the archive copy of this page before it went broken and gather all the information. So what Web Archive does is that it will keep taking snapshots of pages before it went significantly updated or even broken for future users' reference. However, not every case looks good at this. For example, another reference link, the live web page is still working, fortunately. And if you try to click on that, there is a cool image carousel where you can swipe around to see all the cool images within this cave. But unfortunately, if you try to check out its archive copy, you will realize that the carousel functionality is totally broken on the archive copy. So to understand why this happens, we first need to understand how Web Archives operates. It typically operates on 2 pipelines. One is capturing these snapshots, the other is serving them. So capturing snapshot is pretty much similar to how the browser will crawl a page, where you launch a browser, you navigate to the host like cdn.com, you gather the HTML of the page, parsing for dependencies, requesting to the sub-resources like images, JavaScript, and CSS. And with the emergence of JavaScript on modern web today, we also need to run JavaScript to trigger all the JavaScript initial fetches like AX fetches. During this process, the archive system will also try to gather all the responses it received and compile them into a work file, which is the format for Web Archives. To serve such snapshots, the most straightforward way is just to directly serve these responses. But this won't work, and I will tell you why. So let's imagine we want to now get a snapshot of this page. So similarly, we launch browser asking the archive host to give us a snapshot. It gives us a raw HTML, like the original HTML. We parse it and ask for more dependencies. But here's the problem. Because we're giving an original HTML, which has all the embedding link to the original host, now the browser will actually fetch the sub-resources from the original host. And similarly, later on, it will also run JavaScript trying to fetch its AX fetches from the original host. But given that we're asking for snapshots, we don't really want to get this live resource again because they could also be broken or significantly updated. So we want to actually get these resources from archive hosts as well. And in order to do that, the archive system needs to rewrite these sub-resources. For example, first, we need to rewrite HTML so that all the embedded links are now pointing to the archival version of the page, these sub-resources. But also, given the emergence of JavaScript, we also need to rewrite JavaScript so that all the AX fetches are also redirected to the archival host. But this part is actually very challenging because you can imagine there are so many different ways a JavaScript can trigger a fetch. So we need to cover all of such cases to handle these redirections. And also, given that, making sure that they're still compatible with the existing JavaScript runtime. So unfortunately, this cannot be done perfectly with today's archival system. As a result, we are seeing a lot of incorrect JavaScript rewrites that leading to missing page contents. For example, here, if you compare the live web page versus archive copy, you will see that the blog post has a lot of missing images in the archive copy, not because these images are not crawled, but because during this loading the archive copy, there is incorrect JavaScript rewrites that lead to an exception being thrown, and that prevents all the JavaScript to be running, and also which prevents the page rendering to be finished. The problem is not limited to appearance differences, but also in functionalities where if you try to look at this case, for this live web page, if you try to hover on this program button, there should be a drop-down showing different programs. But if you try to do the same thing in the archive copy, there will be no dropdown. The reason is similar. Because we rewrite JavaScript incorrectly, we trigger some errors that prevents the event listener to be added to the button. So given these problems, today's archival system actually already tried to do something to detect these low fidelity archive copies. And it typically involves, you need to crawl the live web page once, you need to crawl the archive page once, and then you compare them head to head. More specifically, the browser needs to crawl the live web page to get the work files and stuff. And afterwards, it actually needs to crawl to gather all the crawl logs, like the errors it encountered during loading, and also some of the representation of the web page, like screenshot of the page. And also need to gather the same set of things from the archive copy. It needs to compile them into work files, upload to replace server, and then it can load the archive copy to gather the same logs for the archive copies. Then it will compare these two logs head to head to see if the page has any fidelity problems. If it does, it will notify developers to pinpoint where exactly is the problematic rewrites. So our system, FidEx, which stands for Fidelity Violation Exposure, tries to optimize this whole pipeline by making a pinpoint automated and also improve the detection. So first, as I mentioned, pinpointing today is a pure manual effort. Developer has to look into them manually to figure out where exactly is the problematic rewrites. So we want to automate this process with FidEx. How can we do that? Well, the most straightforward we can think of is just to learn from the previous two examples I've shown by checking if the archive copy has any extra errors during loading, because that's the previous two cases I've shown. This method, although straightforward, we see it has two limitations. First, a lot of times we see runtime errors doesn't really lead to fidelity violations. For example, if you have some syntax errors for unused libraries, or you have some strong exceptions on analytical scripts, these errors doesn't really matter to how a page renders as an archive copy. And if you start looking into these cases, even if you can fix them, you won't be able to fix these fidelity violations. But the problem also lies the other way around, where many times we see fidelity violations, but there are no runtime errors at all. Like for example, in this case, for this google.com archive copy, if you try to click on add button, there will be a fail to load dropdown. But if you try to check out the console log, you will see it's pretty much empty. This is because there are some semantic errors maybe happen down below, or there are some exception being thrown by JavaScript, but also handled and called silently by native JavaScript codes. So it's really hard for developer to even start looking into where things go wrong. So given these two challenges, our system FidEx actually tried to automatically diagnose these problems. But given the limit of time, I will skip this part. Feel free to check them out in our paper. And I want to focus on a more fundamental problem. That is, so far, we're assuming that this archival system can accurately detect if a page has any fidelity violations. But even that is not doable with the archive system, because they typically rely on pages, like screenshots of pages to compare to see if the fidelity has any problems. But issues with today's representation of pages, like screenshot, is that today's page has become much more dynamic. So for example, there are a lot of videos or GIFs or animations on the page, and depending on when you're taking the screenshot, even on the same page load, you are likely to get very different screenshots. So as a result, we will see a lot of false positives. Basically, the archive system says there's a problem with a lot of pages, but if you manually validate them, they're all just varying screenshots. So we want to actually get a better representation of pages that we can match across. So far, I hope my talk has been straightforward to follow, because starting from next, we're going to dive into some technical details, so please buckle up. So in order to get a better representation of a web page for us to compare, we first need to understand how web browser renders the page. And this is called critical rendering path. It mainly has 4 stages. First, the browser needs to run through network to fetch all the resources. Then the browser will build 2 trees. One is DOM tree, which contains all the elements on the page. The other is CSOM tree, which has all the styles for different classes of elements. During the meanwhile, JavaScript can always be run at any time, making changes to these 2 trees. And whenever a DOM tree and CSOM tree is initialized or changed, the browser will compile both of trees into a layout tree. That will be the final layout specifics for all the visible elements on the page. And whenever layout tree is initialized or changed, the browser will kick in the painting phase that actually paint pages pixel by pixel for users to see. So if you think about where screenshot sits, it actually only captures the very end result after painting. And this is problematic, because at this stage, given the pixel difference, it's really hard for anyone to tell if this is coming from some kind of animations, videos, or if this is actually coming from some missing components that we care about. Instead, what we should be looking at is the stage 2 and stage 3, where in stage 3, a lot of animations and components still have the same layout specifics, so they can still be matched across. But also remember that JavaScript can also be making any change in the layout tree by changing the DOM/SysOm. We also need to keep track of all the JS write that happens to DOM/SysOm during loading. To put them into more detailed example, let's still consider these two examples, where for this left-hand side citizen.com, although there's a video that keeps changing pages appearances, if you try to extract this layout tree, it always has the exact same layout specifics with unchanged layout tree. So you can still match across between the live and archive copy, as long as there's no problem with the page. Simply matching layout tree doesn't work on the right-hand side, because this typewriting effect is actually implemented by JavaScript, keep making changes to the text within the search bar. So its layout specifics also change from time to time. However, as I mentioned, if you are able to track the JavaScript write that happened to the layout tree and track which line of code is actually making changes to this typewriting search bar, you will realize that there's always a single line of code in JavaScript that keeps making changes to the text within the search bar, which has exact same stack traces over time. So by able to associate JavaScript writes with elements, we're able to still match elements between live and archive, even if they have different layouts, as long as they have the same set of JS writes. So in FidEx implementation, we actually combine both of the layout tree matching and set of JS writes to achieve for the best results. So to evaluate FidEx, we run this on 80,000 pages, which are sampled from top 1 million sites with 5 pages per site. And we also introduced 2 detection baselines. One is screenshot matching, which are widely used by today's archival systems, quality assurance tools like browser tricks. And we also introduced another baseline that are kind of trying to mimic how humans are starting doing this by check out if the archive has introduced any extra errors during loading, and we call this small errors. We also bring this small errors baseline into diagnosis, where developer maybe can trying to reason about these extra errors as the source of the problem. So for detection, this figure shows the positive rates reported by each metrics, meaning that how many times these metrics say there's any problematic archive copy. So as you can see, FidEx actually has the lowest positive rates. So that this means FidEx only able to discover the minimum number of fidelity violations. Well, that's not the case, because we also need to think about the false positive rate, meaning that how many times each matrix wrongly says there's a fidelity violation while there's actually no fidelity violations. And if you compare that, FidEx can reduce a lot of false positive rate, even compared to a lower baseline, we're able to reduce false positive rate by 50%. So that means FidEx is just more accurately reporting if a page has any fidelity violations. So we also have the ability to diagnose where's the root cause. So we run this on all the pages that we detect as fidelity violations to pinpoint for the root cause, and then we group them into different group of errors. So this figure shows the distribution of the number of group of errors we see. So the y-axis is the cumulative fraction of pages, and the x-axis is the number of group of pages with same errors. So each of the vertical bump will be a group of errors, or a group of pages with same error. For example, take a random point. This can be interpreted as around 50% of pages are actually within only 2 error groups, the 2 most common error groups. So from this figure, there are clearly 2 takeaways. First, if you look at the right-hand side, we have a long tail around like hundreds of groups we need to fix if we want to fix everything that we can detect. But also, if you don't want to do that, the other takeaways is that if you look at the left-hand side of the figure, by only fixing the top common 4 errors, we're able to resolve more than 60% of the pages. So to leverage from that observation ourselves, we try to benefit that by providing fixes on PyWB, which is one of the most popular open source archival systems, and we provide fixes for these top 4 errors we see. And we're able to fix around 64% of target pages into these 4 bins fully. And thanks to FidEx, a more accurate way of detection, we're able to say that we're not breaking any new pages after these fixes. As a result, we're able to reduce the fraction of fidelity violation overall from 50% to 9% for PyWB. So to summarize, replay on archive copies need to rewrite this JavaScript because we need to reroute the sub-resources. But this is actually a more challenging task than people are Then we think, and as a result, we see a lot of erroneous rewrites lead to fidelity violations. And motivated by this problem, we design and implement FidEx that automatically detects fidelity violations accurately and pinpoints erroneous rewrites for developers to fix. That concludes my talk. Here's the link to our repo. Thank you very much. I'm happy to take any questions.